Cuando quieras, René.
Good morning, everybody. This is another colloquium by the Instituto de Astrofísica de Andalucía in Granada, in Spain. And today we will have the talk by Professor Andreas Eckart, and he will talk about the relativistic phenomena at the center of the Milky Way. Professor Andreas Eckart will be properly introduced by Dr. Isabel Marquez. Please, Isabel.
Thank you, René. Hello, good morning or afternoon, everybody. Thank you very much for being here again. This is another Severo Ochoa colloquium. Thank you all, and thank you, most of all, thank you to Professor Andreas Eckart, who accepted our invitation to be here with us. It's a great pleasure for us to have him here. Professor Dr. Andreas Eckart made his PhD at the Max Planck Institute for Radio Astronomy in Bonn in 1984 about the investigation of properties of extragalactic radio sources. The next 2 years, he had an Alexander von Humboldt Fellow at Stewart Observatory in the University of Arizona in Tucson in the United States. And later on, and until 1999, he worked as a research staff scientist in the submillimeter infrared group at the Max Planck Institute for Extraterrestrial Physics. I said in English, in German, it's not able to say, in Garching. And since 2000, he's professor of physics at the University of Cologne in Germany as well. From 2001 to 2019, he was the managing director of the Institute of Physics at the University of Cologne. And since 2006, he's external member of the Max Planck Institute for Radio Astronomy. And he's also scientific member of the Max Planck Society. His scientific interests cover the determination of the properties of Sagittarius A star from a multi-wavelength perspective, from radio to X-rays observations, and devoted mainly to determining the accretion and outflows and the stellar dynamics near the Sagittarius A star as well. He also studies star formation in the Galactic Center, the molecular gas distribution and dynamics in the nuclei of nearby active galaxies, and the conditions for star formation in nearby AGN and Quasar hosts. He is author of more than 330 referred papers with more than 18,000 citations. Moreover, he also works for instrumentation, and at this respect, he has participated in the development and implementation of a sharp speckle camera at the ISO NTT, which was fundamental for the discovery of the first stellar orbits around Sagittarius A star. He's member of the Scientific Council and Executive Board of the German Center for Infrared and Optical Interferometry, FRINGE, if it is pronounced correctly. And he's also a member of an international collaboration to build the near-infrared imaging beam combiner link Nirvana for the LBT, for the Large Binocular Telescope. He's co-investigator of the VLTI beam combiner Gravity and German co-investigator of the European camera team for MIRI on board James Webb Space Telescope. He has deserved several awards already, some of those very early in his career. For instance, in 1984, the Otto Hahn Medal awarded by the Max Planck Society. In 2004, the Mann-Sieban Medal awarded by the laboratory with the same name in Stockholm University in Sweden. In 2019, the Breakthrough Prize in Fundamental Physics as a member of the Event Horizon Telescope collaboration. And this year in 2022, the Ernst Mach Medal of Honor by the Czech Academy of Sciences for lifelong contribution to the physical sciences. Today, he's talking about relativistic phenomena at the center of the Milky Way, and we have the pleasure of having him here. Thank you very much, and we change seats.
Yeah, thank you for the nice introduction. And I will do my very best to give a nice talk with this on this subject, relativistic phenomena at the center of the Milky Way. And let's first introduce the Milky Way a little bit You all know about it. It's a spiral galaxy that we're living in, and we're about 8 kiloparsecs away from the center of the Milky Way. That means we have to look through all the dust and gas over 26,000 light years. And that implies that there is an extinction in the optical of about 30 magnitudes. Therefore, you better study it in the infrared, where the extinction is only of the order of 3 magnitudes. Of course, you can also do it in the radio and in the X-ray domain. And you have to go to the south because it's a southern object. So here, if you would like to do it here from Granada, it would only be like 7 or 8 degrees above the horizon or something like that. So that's not very useful. Then the center of the Milky Way consists of a stellar cluster, late type and early type stars. And if you go to the very center in the vicinity of the supermassive black hole, you find a cluster of high velocity stars that has been subject of several investigations. A few are listed here. And from this, you can derive the central mass of the black hole as 4 million solar masses, actually. So this is the points that I would like to put forward. I will talk a little bit about the instrumentation, only very, very briefly, just giving names basically. Then I will talk about the periastron shift and the gravitational redshift of the star S2. I will then go into other stars, further stars, S stars. So S stars are the high velocity stars. So we just named them one after the other, and S stands for Stern, star. So S1, 2, 3, and so on. So the S-star cluster is the high velocity cluster. So I will introduce a few interesting candidates that we found recently that are on very elliptical orbits, and we will see that most of them also are relativistic objects, at least during the periaps. We'll talk then about the bulk motion of plasma orbiting Sagittarius A star, and we will see that that is also a relativistic phenomenon, of course. And finally, we will go into the emission process a little bit. We'll talk about the relativistic electrons that give us most of the radiation that comes from Sagittarius A star. Instrumentation. So as mentioned already in the introduction, a great deal of observations was done both with the NTT in La Silla, but then starting in 1999, 2000, we used the 8-meter telescopes on Paranal. And also then recently the interferometer that combines mainly the 4 large 8-meter dishes. So most of the investigations were done with the UT4, because that harbored the spectrometer and the imager, the adaptive optics imager. Gravity, the interferometer, is a very important tool right now to study the stars in the center of the Milky Way, and also other sources in the sky, other nuclei, and also other stellar sources all over the sky. Principal investigator is Frank Eisenhower from MPE in Garching. And the First Physics Institute at the University of Cologne is an important collaborator here. So we came up with the 2 imaging, or with the 2 beam combiner spectrometers that we built for the instrument. And then, of course, I will also mention some X-ray data, which is very important if you want to study activity of Sagittarius A star, in particular the flares. And those data were taken with Chandra and with XM and Newton. So the prime instruments that are being used for faint sources. Periastron shift and gravitational redshift of the star S2. Let's first talk about the phenomenon as such. Since a heavy mass modifies space-time, it means that in reality, a star cannot be on an elliptical orbit. Elliptical orbit would be a closed orbit. That would be a Newtonian solution for the problem. But actually, including relativity and the space-time deformation, you produce a Rosetta shape orbit. So a periastron shift is imposed for each flyby of the source. That means the orbit is no longer closed. So that is the dominant effect if you talk about very, very heavy masses. There is another periastron shift that is due to extended mass, and that would be the retrograde Newtonian periastron shift. So not only does the source see effectively a different potential underneath itself due to relativity, but also due to the fact that it may resolve an extended mass contribution. So if the star dives down towards periaps, it suddenly sees less mass under it. So it gets attracted by less mass. So the potential has changed, and that again leads to a periastron shift. Interesting to note is that the Newtonian periastron shift is retrograde. So it goes the other way. So in principle, you could think of a scenario in which the prograde and retrograde shifts compensate each other. So therefore, you have to make sure that you know what you do and that there is no large extended mass around. For the Galactic Center, we can be relatively sure that there's not a large extended mass contribution. Various groups, including our own group, have put limits on it. And the typical limit is of the order of 10 to the 4, and maybe even now a few times 10 to the 3 solar masses of extended mass that could be there given the uncertainties of the mass measurement. But effectively, we think that there's very, very little extended mass that we have to worry about. In addition, you have another third effect, which SgrA in 2012 pointed out. That is, if you have an extended mass, it doesn't necessarily have to be very fine in composition to be extended. It could be very granular. For instance, you could have 20 solar mass black holes, which are not luminous, and they could make up the extended mass. And then you would have a granularity of an extended mass. That also means that the potential underneath the star changes, but now in a stepwise way. But effectively, that can also change the orbit. And you can think of scenarios in which all these three phenomena are of equal interest in a way. So in order to study the potential effect of a Newtonian or of a gravitational periastron shift, a relativistic periastron shift, we made use of the fact that the orbit you expect is not closed, is not an ellipse, but a section of this Rosetta-shaped orbit. That means that if you take, for instance, the upper half or the lower half of the orbit and fit an ellipse to it, you get slightly different solutions. Also, you get slightly different solutions if you take the ascending and the descending part of the orbit. And the difference here would then be the periastron shift, delta omega. So you can look at all these elements, eccentricity, long axis, and omega, and they all reflect the non-ellipticity in theory, if you do it right and if you're sensitive enough. In fact, we were able to do that. We were able to find out that the exactness with which the imaging data were taken with NACO was already sufficient to demonstrate that in principle, you can measure the relativistic periastron shift. So the value that we got from that experiment is 14 arc minutes, and expected from the 4 million solar masses would be 11. So quite close. Also, you can parameterize the degree of relativity. And we did that as proposed by Zucker et al. In 2006 by taking the ratio of the Schwarzschild radius and the periapse radius. And that value was expected to be 0.00065, and we got 0.00088. So also very close. So in a way that works. And that actually led to a press announcement in 2017, in which we stated that in principle, the data is present for a measurement of that particular quantity. And what it actually means is shown here. So in that paper that responded from that work, that resulted from that work, we were able to take two sources, which are on slightly more larger objects where the relativistic periastron shift is not important really. That is S38 and S0102. And we basically held on to those orbits and measured the S2 orbit relative to that. And the value that we obtained from the analysis basically shows that the orbit would not be closed, and that is shown here. You see the star does not return on exactly the same orbit, but is a little bit displaced. So, as I mentioned, VLTI gravity is important here because you can do that measurement of the relativistic periastron shift also, and with much higher accuracy with the interferometer. And as I mentioned, this is the consortium that built the gravity instrument. And here is a sketch of the beam combining spectrometers that we built. We built 2 of them. And so we helped in a great way to make that instrument working. So as you can see, it's a complicated system, mostly consisting out of lenses and prisms and prisms. And of course, there's also beam splitting devices in there that subdivide the information into various channels, which are then combined interferometrically. The data as such is brought to a common focus in the beam combination channels, in which the path length difference due to the source drifting on the sky relative to the instruments needs to be compensated. So that is done by mirrors that are positioned on cars that are moved on tracks. And then again, you have voice coils and piezo stacks that do the compensation of the fine compensation of the differential path length that needs to be compensated. And then the light is led to the central instrument, in that case, gravity. And that is here first fringes with gravity. And you can see it's a complex instrument. And you see a person here in comparison. And this is the corresponding measurement of the Schwarzschild precision, so the relativistic periastron shift. As you can see, one had to depend also on earlier imaging measurements, as we did in our analysis. So this block saying NACO here is basically the data that you hold onto. And from then on, you can measure the difference to that data with gravity, and you can see that the path of the data here deviates significantly from the NACO data. And that is due to the relativistic periastron shift of exactly the same amount that we were talking about earlier. There's not only the relativistic periastron shift, but also the gravitational redshift, which is of importance and which reflects the degree of relativity in the motion of that star, that particular star S2 as well. So that is the light becomes redder due to the influence of the gravitational potential. Mathematically, this is expressed in this version here. So the redshift Z, that is delta lambda over lambda, can be written out in a potential series with beta. Beta is V over C, so the velocity in terms of velocity of light. And the important term here is the B2 that is standing in front of the B squared term. And the B2 contains B2D and B2G, which is the gravitational redshift and the special relativistic transverse Doppler effect. Both come in with the same weight of 1/2, and you cannot distinguish between them. So you measure always the combination. But in any case, if you measure something, you know half of it is the gravitational redshift, and the other half is then the transverse Doppler effect. And the amount that was expected was measurable with standard spectrometers. So the delta lambda over lambda that you can come up with due to this B2 terms is of the order of 10 to the -4, which can reasonably easily be reached with spectrometers. And that would imply that due to the redshift, the position of a line, for instance, would be shifted by the amount given here of 150 to 200 kilometers per second. And that would be the expected curve, the deviation in velocity. And this is the data. This is the actual measurements. On the right-hand side, you see the result of the gravity collaboration. You see that the rise was exactly as expected, and then the source started to descend. So the effect was getting weaker, and the paper was written somewhat faster here. In comparison to the UCLA group on the left-hand side. So they waited until the data really showed that it came back close to the earlier velocity measurements. But the amount of deviation that was expected, namely the 150 to 200 kilometers, was clearly reached. So the effect of gravitational redshift, as expected from relativity theory, could be proven here. Now, S2 is an interesting object, but it has quite a long orbital timescale of about 15 years or so. And that makes it some sort of difficult to do repeated measurements. So the interesting question is, are there other stars nearby, near the supermassive black hole? And indeed there are. So there's a number of papers out here by Peisker, for instance, in which we published the existence of such stars. So it started with S62, and then we got into other stars. So this is S62, which is on a highly elliptical orbit. As you can see, it is rather difficult to identify that source. So you have to stare for a long time at these images to find these objects. And also the images shown here are not, by far not all of the images that we looked at. So we have multiple images for individual epochs. In any case, you can actually find these sources and you see them moving. And if you plot what you see, here's another case, then it gives also a very nice elliptical orbit. Here's another case that we then found, again, here encircled in white dotted dashed lines, and S62, I think here is given in green color. And we then started to give these sources Cologne names. So we started here with S4711. And if you have been in that region, you know that 4711 is a very famous perfume that you can buy in Cologne that is originally from Cologne. I actually talked to the company whether we are allowed to do that, and they said, no problem. If you don't mention this, then you can use that. So we named that star S4711, and from then on, we named other stars starting with that number. That is S4711, as you can see in the RA and DEC plot and in the on-sky ellipse, that the data quite nicely represents an elliptical orbit here as well. This is S4712 now, 13, 14, 15, and this is S4716, which is an interesting source. It is actually the source with the shortest orbital timescale right now. So that has an orbital timescale of only 4 years. So basically every 4 years, you will be able to do these relativistic measurements. And we are looking forward, or some of us are looking forward to do these measurements with the large telescope, with the 40-meter telescope, which has a much higher point source sensitivity than the 8-meter telescope. So that's going to be great fun to do that. And this is the identification of 4716. So this is the, as to my knowledge, best identified high velocity star in the S-star cluster. If you look at all these individual data points in RA and DEC, that all fall onto the very same orbit that S4711 has. And not only positional orbit points, here magnitude doesn't deviate too strongly, so it's the same source that we're looking at. Also, the spectroscopy can be done, and you can take the Beckett gamma line, for instance, and determine the velocity of the star. And there's actually two epochs where the star is sufficiently isolated that you can get its particular spectrum. And those, one is close to periaps and one is close to apoaps, and those are located at the right velocities. So the orbit is also velocity supported. So that is S4716. And this is the on-sky data. You see that we have in black imaging data in periaps, also a lot of imaging data in apoaps, more there, of course, because the source is slower there and spends a larger amount of time in the apoaps. And as you can see, this source is also detected, and that's how we actually got to the source with gravity. So the red data points are interferometric detections. So this star is being measured interferometrically and in imaging and in spectroscopy, and it has an orbit of 4 years only. And that is the solution in a corner plot demonstration. And as you then have the orbit and can set equal the proper motion velocity and the spectroscopic velocity, you can also derive the distance and the mass. And the mass turns out to be 4 million solar masses, and the distance turns out to be 7.93 kiloparsecs, in agreement with other measurements. Here is a list of properties that S4711 has, and as you can see from the corresponding formula at the bottom, you can derive all sorts of interesting relativistic properties of that source. So it has a very high velocity due to in periapse. And there's another list now coming. This is actually all the stars now that are very close, as you can see in the inner plus or minus 0.2 arcseconds surrounding orbiting Sagittarius A star. And here is a little table that also lists the velocities of these stars in periapse. As you can see, they're reasonably fast and come reasonably close to relativistic velocities. Here, V periapse is the periapse velocity. As you can see, thousands, several 10,000 kilometers per second. And 4711 has 2,300. Actually, 23,000 kilometers per second in periapse. So in comparison, S2, the source that was investigated in great detail had only a velocity of about 7,000 to 8,000 kilometers. So these will all be very, very good candidates to do the relativistic periastron shifts and study the relativistic properties of that region. Now we come to the plasma. So we move into the inner region close to Sagittarius A star. So we talk about the bulk motion of plasma orbiting Sag A star. And if you have something orbiting, emitting and orbiting a very heavy mass, then you see all sorts of interesting relativistic effects. In particular, if the source is looked at edge on or almost edge on, then once it approaches the observer, it is Doppler boosted. And once it recedes from the observer, it's Doppler deboosted. It's also shifted in frequency, of course, although that is not the prime target here, but you see periodic modulations in its brightness. And there's actually two effects that are of relevance here. And as you can see here, the observer on the left looking at the black hole. And in this picture, we imagine a source that is edge on, orbiting the supermassive black hole at two different distances from it. There's one position, namely when the source is exactly behind the supermassive black hole, when lensing is of importance. So then you see a boosted intensity due to the lensing effect. So the rays are being bent towards you, so that gives you a brighter appearance, gives the source a brighter appearance. And then depending on the distance of orbit, so the radius, you see these locations D. This is when the Doppler boosted emission will be dominating the emission from the source. And as you can see, this is not exactly behind or not exactly at the site of the source, but due to the fact that the light is bent around the supermassive black hole, you can sort of look around the corner and you see this Doppler boosting, i.e. when the emission is coming towards you, but then bent by the massive black hole at two different positions here. So what you expect is a lensing peak followed immediately by a boosting peak. And you can calculate for various scenarios the light curves that you expect. And you can see they all basically look the same. First, on the left-hand side comes the lensing peak, and then on the right-hand side comes the boosting peak. Now, we looked at X-ray flares. And if you know that, you can actually see it, that some of these flares, or actually we say all of them, have an indication of a lensing shoulder in addition to a Doppler peak. And that is also true for another flare, this Ponti flare on the right-hand side, published by Ponti in 2017, where you can see very nicely a lensing peak in addition to a boosting peak. So that indicates that at least for the brightest X-ray flares, you do see the signature of orbiting, emitting clouds almost edge on. And you can actually make use of this. That's a very interesting topic here, because what we did is we can fit from scale-free light curves theoretically calculated. We can fit those to the observed light curves, and then by introducing the actual time the flare takes, we can remove the scale freeness and scale it. So then we have the light, the flare in seconds. And due to the scaling, we have also introduced a mass. So in other words, by doing this fitting with relativistic, with theoretical light curves, you can actually get back the mass about which that blob is orbiting. And we did that for all four flares. And we get, in fact, a value very close to 4 million solar masses, just from the flare profile. And by the way, we did this also with one extragalactic source in that very paper that also showed some quasi-periodicity. And there you also get back the black hole mass that was there, derived also by other means. So that's a very interesting phenomenon. So that's all consistent. Now, the fact that matter is orbiting Sagittarius A star had been a model assumption, which worked quite well. But then with gravity, for the first time, we could actually see material orbiting. We couldn't really image it, but the effect of a blob emitting and orbiting Sagittarius A star is also that the center of gravity of the emission is shifted. So the interferometer as such has only an imaging resolution of the order of 1 or 2 milliarcseconds, but the positional shift is of the order of a few 10 microarcseconds. And that is sufficient to actually do that measurement. And here you can see on the left-hand side the X and Y component of the measurement in addition to the black light curve. And on the right-hand side, you can see the positions on the sky. And you can see also the central orange position of Sagittarius A star. And you see that in that case, and I think in 1 or 2 other cases as well, more or less, a nice orbiting track could be proven, could be identified. So that for the first time gave true imaging evidence that actually matter is orbiting Sagittarius A star. Interestingly enough, with that method, one finds blob orbits which are more face-on rather than edge-on. So it's very likely that both families of flares exist, that sometimes the blobs are orbiting face-on and sometimes they're orbiting edge-on, depending on where they came from and how they descended to Sagittarius A star. So all of this is nicely spelled out in various publications. That, of course, brings us to other imaging methods that can depict, they can make pictures of material very close to supermassive black holes. And the prime candidates here are, of course, Sagittarius A star and M87, which are the largest black holes in the sky, supermassive black holes in the sky. And for M87, it was a little bit easier, quote unquote, to do that measurement because it's a much more massive source, 1 billion times more massive, and also a larger source, but therefore it's also further away. But as a consequence, it has approximately the same size, as you can see, about 50 microarcseconds on the sky. And here it could be shown that one side is actually brighter than the other, indicating that Doppler boosting is probably going on here as well. And that can then very nicely put into the other dynamical information that is obtained and known for M87. For Sagittarius A star, it was a little bit more complicated because the source is variable, is smaller and therefore also more variable in comparison to M87. And this is something interferometrists don't like. While they're busily trying to fill up the UV plane, when the source varies at the very same moment, then you mix up variation information with structural information. And that's very bad. But in any case, various mapping algorithms have been developed and have been compared, and they all show similar structures. And then in the end, one could combine all the imaging information and retrieve the image on the left-hand side. However, at the cost of a problem here, that is, it is not that nicely shown as in M87 that something is in orbit and that some side is brighter. You have 3 bright dots on here, and we don't know, or it is not known at the moment, what these 3 bright blobs are and whether they will stay or not, and so on. So it needs to be measured again and repeatedly. We now come to the after we now talked about stars and about plasma blobs, so physical objects that move with very high speeds relativistically, we can now go to the smaller particles, namely the electrons. We don't talk about the protons, which are certainly there as well. But the electrons are cooling much more massively, since they are 2,000 times lighter than the protons, and therefore they are brighter. So the relativistic electrons are of interest. So if you look at the overall spectrum of Sagittarius A star, here depicted on the right-hand side, you see in this plot, this is a nu L nu versus log nu plot, that it has a rising, in that representation, a rising radio spectrum, and then a relatively flattish, slightly descending spectrum towards the infrared and X-ray domain. And that there's certainly structure and variability as well. So the question is, what is it? Who is radiating here? What mechanism is of relevance? And one finds, I can summarize this here, that in the radio part, longwards of a few millimeters, it's mostly synchrotron radiation and potentially also some Bremsstrahlung that is of relevance. Whereas in the short wavelength domain, it is mostly synchrotron radiation, and then in the X-ray domain, most likely also synchrotron self-Compton radiation that is of interest here. So as a short reminder, what synchrotron radiation is. So synchrotron radiation, the photon measure of synchrotron radiation basically reflects the spectrum of the energy spectrum of relativistic particles. So if you have relativistic particles that ideally go from gamma 1 to gamma 2 with a power law, the power law spectral index P, then that power law spectral index P is reflected in alpha in the optical thin part, and alpha and P are related by pi equals 1 plus 2 alpha. The problem in the optical domain, in the radio, in the photon domain, however, is that you have self-absorption. So therefore, at the location where tau becomes 0, or tau is of relevance, then you have a peak, self-absorption peak. And the spectral index below that is plus 2.4. And above that, with the appropriate spectral index in the relativistic electrons, is of the order of minus 0.7. Now, not only is there synchrotron radiation, but the bulk of the synchrotron photons are being emitted by relativistic electrons and are being scattered by them immediately. So you have synchrotron self-Compton scattering as well. And the Compton mechanism for high energies works opposed to the Compton effect that you know from laboratory physics. In laboratory physics, it is the photon that gives energy to the electron, but in relativistic matters, it is the electron that gives actually energy to the photon. So therefore, the relativistic electrons give energy to the submillimeter photons and scatter them into the infrared or X-ray domain. And that then leads to a spectrum, a synchrotron spectrum, which is Compton scattered to higher frequencies. So that is relevant for the X-ray domain. And if you would talk to a gamma ray observer, he wouldn't even argue that that is of any relevance, because they need Comptonization, as they say, to actually talk about the existence of their photons, which they can count individually. So the spectrum of, and the relativity and the variability of the emission from Sagittarius A star has been investigated in great detail. So I will come to the infrared light curves in a second. But here is, first of all, a very nice paper by Nielsen, in which he basically studied the power spectrum of variability, if you want so. That is the degree of variability as a function of count rate, of brightness of the source. And that has this shape here, approximately. you see very bright flares become rarer compared to very faint flares. But you also see that there is a structure to this. And the structure is basically dominated by the detection effect of the photons on the chip. And what Nielsen found by modeling this emission with a bounded power law, that is a power law with a hard cutoff, that the power spectrum of that underlying variability distribution is 0.99. And we could verify that by reanalyzing the X-ray data that was taken by Chandra, for instance, over a very long stretch, very coherent data set. However, we said, due to a reason that I will point out in a second, that it's highly unlikely that the bounded power law is the right approximation for this, because very rarely in nature you get a very hard cutoff. Most of the quote-unquote hard cutoffs are exponential. So there's an exponential drop. And if you, but that makes the mathematics a little bit more unpleasant here, but you can do it. So then we discussed this in the framework of a truncated power law with an exponential cutoff. And we got a different spectral index, a significantly different spectral index, namely 1.66, which first of all tells you that the errors that were attributed to this alpha did not at that point, also in the Nielsen paper, contain systematic uncertainties due to the modeling approach, because it was not correct, most likely, to have a sharp cutoff. But an exponential cutoff is more likely the right way to do. And that is also done here in the Zubrowite paper. And why is 1.66 so interesting? Because if you look at the formulae which calculate the synchrotron self-Compton spectrum or flux out of the synchrotron spectrum, and if you take all the dependencies there that you can come up with, flux, source size, magnetic field, and so on and so forth, and if you do some assumptions, which I will not spell out here, but which you have to read up, and saying that basically only the variability of the infrared flux is of interest, the infrared flux here depicting the submillimeter flux of the steep spectrum, then you have a certain expectation to the variability spectrum in the X-ray domain. And you can calculate what that expectation is, because then the spectral index of the variability plot in the X-ray domain depends also on the spectral index, the photon thin spectral index. Here is written as sigma of 0.6, so minus 0.6, that is, different notation. And then you get 1.6. So 1.6 is actually the spectral index you would expect from theory under under the assumption of synchrotron self-Compton. And now we have shown that by doing this more improved model approach, we actually do get the 1.6, which indicates that the variability spectra in the infrared and the X-ray domain are fully consistent with the bulk of the flares being due to synchrotron self-Compton. So that does not exclude that some of the flares could be synchrotron in the X-ray domain that would require very fast relativistic electrons, like 10 to the 6, little gamma of 10 to the 6 or so. But most of them are synchrotron self-Compton flares with little gamma of only of 10 to the 4, 10 to the 3, and that you can easily get. So, as I mentioned, most likely, most of the flares are synchrotron self-Compton flares, which implies a slightly higher density, of the order of 10 to the 8, 10 to the 9 per cubic parsecs, per cubic centimeters. But that is fine, because you do need a higher density if you want to explain the rotation measures observed towards the source and other phenomena. So a slightly higher density, and not unrealistically higher density, because for pure synchrotron you have 10 to the 6, 10 to the 7. It's only of the order of magnitude or so more dense is fine. And most of all, it's only moderately relativistic. So little gamma is 1,000, which you can easily reach. So it's great. But that also shows you that in the discussion of the spectrum, the overall spectrum, it is the first peak which is of relevance. So this is the peak where the photon spectrum becomes optically thin in the submillimeter domain, because this is where the highest density of relativistic electrons and relativistic and photons come together and allow for a great deal of scattering. It is not other breaks, cooling breaks at higher frequencies that are relevant for that process here. Because in the nu spectrum, you only discuss the energy, but you do not discuss the scattering efficiency. And if you read up on the theory of synchrotron self-Compton, the scattering efficiency is purely given by the intensities, the photon intensity and the density of electrons. That could now, in a very nice work by Witzel et al., be used. So he produces simulated light curves, and this is one of the way he does that. So he basically starts with random numbers, then chooses the right statistics, and can then also use a synchrotron and self-Compton formalism to modify these synthetic light curves, and then can reproduce the submillimeter light curves, the infrared and the X-ray light curves, and compare them to the observed ones. And they do have statistically the same properties. That's very nice. So basically, in his model, he uses exactly the emission model that I described earlier. So you have the here now shown in L nu versus logarithm nu. You have the synchrotron self-absorption peak of the red synchrotron distribution. Here, the scattering takes place predominantly, and that scatters the spectrum upward to the synchrotron self-Compton scattered spectrum. And that means that most of the flares are actually synchrotron self-Compton in that model. Interestingly, in that region, the overlap region, which is in the infrared, you have another phenomenon. The infrared spectrum sort of turns down at higher infrared energies, so there's a cooling break, and the location of that cooling break may be variable. So it may be more energetic or less energetic. Steepening or non-steepening the infrared spectrum. And in fact, some steep infrared spectra have been observed. Most of them are 0.6, so flattish or synchrotronish, but some of them are as steep as -1, -2 or so. And that had been discussed in a great detail. But this model now allows, that was also derived earlier under different circumstances. This model now includes all of the effects and allows you to reproduce the variability in a very detailed and statistically correct way. And the inclusion of the synchrotron self-Compton mechanism in this formalism described by Witzel now also allows him to include adiabatic expansion and adiabatic compression of clouds, giving modifications to the rising and falling side of the flares. And he spelled that out, how that can actually be used, and then has this cycle of adiabatic expansion and then in compression and injection again. So which is shown here on the right-hand side. So that is one flare. And you have probably several flares going on at the same time and being mixed up in the infrared domain. That's why for the very brightest flares, you can study the individual flare shapes best because they are more isolated than the fainter flares. Now, having said all of this, having looked at the stars and the orbiting gas blobs, we can now see what that means for the enclosed mass. We always get 10 to the 4 million solar masses. So you see that the enclosed mass plot that comes here from parsec distance from the CND and from the late type stars in the outer regions of the cluster comes down to the flat part when you're being dominated by the supermassive black hole. Again, also indicating that the amount of extended mass is likely very, very minute. So we are truly dominated by the central massive black hole. And you can also put this in this graph. This basically shows the mass, and plotted against the mass is a space curvature, a degree of relativity, basically. And you can see if you are at 0 here, you are then at the black hole horizon. And as you can see from terrestrial labs in the lower left, we made our way all the way through Mercury and pulsars now to supermassive black holes, and have here now the Parser paper and the gravity paper on relativistic periastron shift, We have the SgrA paper on very high, fast-moving stars, S62 as an example. And we have the X-ray hotspots in the Carson paper that allow you to look at the flare shape with the lensing shoulder. And we also have the gravity measured infrared hotspots. So all of this comes very close now, huge Schwarzschild radii only to the event horizon. So we are very close in and can measure the relativistic environment of the supermassive black hole. So basically, orbiting stars and plasma allow us to probe the relativistic environment of Sagittarius A star in great detail. And we'll continue to do that. So Cologne has been built flight hardware, an imaging spectrometer actually for James Webb. So this is flying and working. And we are eagerly waiting for Galactic Center data that has been taken and will hopefully then be taken also with NIRI in the mid-infrared for us and for the community. And we are also building a calibration unit for the ELT METIS instrument. So we are involved in this instrumentation as well, which then allows us to have access to imaging data with which we can also study the environment of Sagittarius A star. That was it. Thank you very much. I guess there are questions.
Thank you very much, Professor Hector. Yes, please, if there is any question in the room, maybe can be managed by Francisco or Rainer.
Yeah, good. Well, first of all, thank you very much for the talk. I would like to know, besides the stars that have been observed and are still being observed very close to the black hole, is there a low mass population not bright enough to be detected?
Most likely, yes, but we don't know because we haven't detected it yet. It's of lesser importance concerning the luminosity and the mass contribution. But a paper that discusses that in great detail is written by SgrA. If you look up SgrA et al., she goes in with the mass and luminosity function and looks what the limitations are with these measurements. Yes, yeah. All of these stars are only the tip of the iceberg, most likely. On the other hand, we don't know how many fainter stars there are very close in, because you can think about dynamical processes that kick those stars out. So we don't have the answer. But we can speculate about it.
I have a naive question. First, thank you very much for the nice presentation. As far as I know from hydrodynamical simulations in young stars, when there are several components, at least 3 components, one of the components could be ejected, the lower mass component. I am wondering if it could happen in the case of the Galactic Center because you have many components, or if you can detect or
it may happen. It may happen. We haven't observed it positively, but it may happen. And actually, one of them, that mechanism is actually being discussed to explain the presence of the S stars in the vicinity of the black hole, because these S stars, they are O stars, and with properties very much like O star population in the vicinity of the sun. So they're normal O stars, but that means they are reasonably young. And the question is, how did they get there? Right? Because normal star formation doesn't work. And you cannot form them outside and bring them in, because then they become too old already. So they must have been formed in situ. But there are ways to do that. There is a paper by Jalali, for instance, that assumes that, that due to collisions, a gas cloud, a cool gas cloud from the circumnuclear ring descends towards the supermassive black hole. And if it does so, it goes in orbit, and then you have kinematically an orbital compression, which can push the density over the required density to form a star, and you can form main sequence star supported by the gravitational field of the supermassive black hole in the very vicinity, and then some of them stay there. So that is possible. But the other mechanism, that's why we're talking about this here now, that gives the stars, the young stars to the center, is that maybe they have been formed in binaries, or there was a binary collision, and then one was ejected and the other one lost energy and sank down into the region. So all of this may be of importance, but we don't have the real answer. We can talk about it. So,
I think Isabel had a question.
Yes. With the advent of new instrumentation that we have for the next coming years, do you think that we have any hope of using extragalactic objects or other galaxies and ourselves to make similar or somewhat similar studies?
It's going to be very difficult, because you cannot beat the 8 kiloparsecs. So we are in a very special situation here. So I doubt that similar studies with this high angular resolution can be done in nearby objects. So it doesn't work, for instance, in M33. You don't get that close, for instance. So we have to stick with this one case that we can study in great detail. Which doesn't mean that one can apply these techniques. One gets closer in, but not as close as here in that case.
One of the 4711 stars, does it fit completely into the field of view of gravity? Like this 4-year period star, can you follow it?
No. It goes into the field of view of gravity and then it goes out again. So
how far does it go out?
I would guess like 2 or 3 field of views. Yeah. At least one.
2 arcseconds,
yeah.
more or less.
Yes.
Okay. Any other question? By the way, I would like to mention, so if in case you're interested in other things, Andreas is also a great knower of the Arab world, and he actually translates astronomical texts from Arabic into English and then collaborates with Arabic universities. So in case you have interests there, you're very welcome to discuss this with Andreas.
Interesting things can be said there as well. Yeah.
We will go to dinner tonight, so anyone who, I have not yet decided where and when exactly, depends on if somebody wants to come along, we currently people from my group, let me know as soon as possible, because eventually I have to make a decision where and when. And yeah, thank you very much, Andreas, for coming here. Andreas will be staying until Friday if you want to discuss with him. He's in Anton's office at the moment. So thank you very much.